Phosphorus.
Phosphorus is a non-metallic chemical element with symbol P and atomic number 15. A multivalent pnictogon, phosphorus as a mineral is almost always present in its maximally oxidized state, as in organic phosphate rocks. Elemental phosphorus exists in two major forms, white phosphorus and red phosphorus, but due to its high reactivity, phosphorus is never found as a free element on Earth. The first form of elemental phosphorus to be produced, white phosphorus, in 1669, emits a faint glow upon exposure to oxygen, hence its name given from Greek mythology, phosphoros meaning light bearer, Latin Lucifer, referring to the morning star, the planet Venus. The term phosphorescence, meaning glow after illumination, originally derives from this property of phosphorus, although this word has since been used for a different physical process that produces a glow. The glow of phosphorus itself originates from oxidation of the white, but not red, phosphorus, a process now termed chemiluminescence. The vast majority of phosphorus compounds are consumed as fertilizers. Other applications include the role of organophosphorus compounds in detergents, pesticides and nerve agents, and matches. Phosphorus is essential for life. As phosphate, it is a component of DNA, RNA, ATP, and also the phospholipids that form all cell membranes. Demonstrating the link between phosphorus and life, elemental phosphorus was historically first isolated from human urine, and bone ash was an important early phosphate source. Phosphate minerals are fossils. Low phosphate levels are an important limit to growth in some aquatic systems. The chief commercial use of phosphorus compounds for production of fertilizers is due to the need to replace the phosphorus that plants remove from the soil, and its annual demand is rising nearly twice as fast as the growth of the human population.
Characteristics. Physical.
Phosphorus exists as several forms, allotropes, that exhibit strikingly different properties. The two most common allotropes are white phosphorus and red phosphorus. Another form, scarlet phosphorus, is obtained by allowing a solution of white phosphorus and carbon disulfide to evaporate in sunlight. Black phosphorus is obtained by heating white phosphorus under high pressures, about 12,000 standard atmospheres or 1.2 gigapascals. In appearance, properties, and structure, it resembles graphite, being black and flaky, a conductor of electricity, and as pucker sheets of linked atoms. Another allotrope is diphosphorus. It contains a phosphorus dimer as a structural unit and is highly reactive.
White phosphorus and related molecular forms.
The most important form of elemental phosphorus from the perspective of applications in the chemical literature is white phosphorus, often abbreviated as WP. It consists of tetrahedral P, 4 molecules, in which each atom is bound to the other 3 atoms by a single bond. This P,4 tetrahedron is also present in liquid and gaseous phosphorus up to the temperature of 800 degC when it starts decomposing to P,2 molecules. Solid white exists in 2 forms. At low temperatures, the B form is stable. At high temperatures the A form is predominant. These forms differ in terms of the relative orientations of the constituent P4 tetrahedra. White phosphorus is the least stable, the most reactive, the most volatile, the least dense, and the most toxic of the allotropes. White phosphorus gradually changes to red phosphorus. This transformation is accelerated by light and heat, and samples of white phosphorus almost always contain some red phosphorus and accordingly appear yellow. For this reason, white phosphorus that is aged or otherwise impure, for example weapons-grade not lab-grade WP, is also called yellow phosphorus. White phosphorus glows in the dark, when exposed to oxygen, with a very faint tinge of green and blue, is highly flammable and pyrophoric, self-igniting, upon contact with air and is toxic, causing severe liver damage on ingestion. Owing to its pyrophoricity, white phosphorus is used as an additive in napalm. The odor of combustion of this form has a characteristic garlic smell, and samples are commonly coated with white, D, phosphorus pentoxide, which consists of P, 4O, 10 tetrahedral with oxygen inserted between the phosphorus atoms and at their vertices. White phosphorus is insoluble in water but soluble in carbon disulfide. The molasses, cracking, of P4 at 1100 Kelvin, gives to phosphorus, P2. This species is not stable as a solid or liquid. The dimeric unit contains a triple bond and is analogous to N2. It can also be generated as a transient intermediate in solution by the molasses of organophosphorus precursor reagents. At still higher temperatures, P2 dissociates into atomic P. Although the term phosphorescence is derived from phosphorus, the reaction that gives phosphorus its glow is properly called chemiluminescence, glowing due to a cold chemical reaction, not phosphorescence, re-emitting light that previously fell onto a substance and excited it.
Red phosphorus.
Red phosphorus is polymeric in structure. It can be viewed as a derivative of P4 wherein one pp bond is broken, and one additional bond is formed with a neighboring tetrahedron resulting in a chain-like structure. Red phosphorus may be formed by heating white phosphorus to 250 DEGC, 482 DEGF, or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. In this sense, red phosphorus is not an allotrope, but rather an intermediate phase between the white and violet phosphorus, and most of its properties have a range of values. For example, freshly prepared, bright red phosphorus is highly reactive and ignites at about 300 DEGC, though it is still more stable than white phosphorus, which ignites at about 30 DEGC. After prolonged heating or storage, the color darkens, see infrabox images. The resulting product is more stable and does not spontaneously ignite in air.
Violet phosphorus.
Violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 DEGC. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, a red-purple form is obtained. Therefore this form is sometimes known as Hittorf's phosphorus, or violet or a metallic phosphorus.
Black phosphorus.
Black phosphorus is the least reactive allotrope and the thermodynamically stable form below 550 DEGC. It is also known as bimetallic phosphorus and has a structure somewhat resembling that of graphite. High pressures are usually required to produce black phosphorus, but it can also be produced at ambient conditions using metal salts as catalysts.
Isotopes.
23 isotopes of phosphorus are known, including all possibilities from 24P up to 46P. Only 31P is stable and is therefore present at 100% abundance. The half-integer nuclear spin and high abundance of 31P make phosphorus 31nm spectroscopy a very useful analytical tool in studies of phosphorus-containing samples. 2 radioactive isotopes of phosphorus have half-lives suitable for biological scientific experiments. These are 32P, a beta emitter, 1.71 MeV, with a half-life of 14.3 days, which is used routinely in life science laboratories, primarily to produce radiolabeled DNA and RNA probes, for example for use in northern blots or southern blots. Because the high-energy beta particles produced penetrate skin and corneas, and because any 32P ingested, inhaled, or absorbed is readily incorporated into bone and nucleic acids, Occupational Safety and Health Administration in the United States, and similar institutions in other developed countries require that a lab coat, disposable gloves and safety glasses or goggles be worn when working with 32P, and that working directly over an open container be avoided in order to protect the eyes. Monitoring personal, clothing, and surface contamination is also required. In addition, due to the high energy of the beta particles, shielding this radiation with the normally used dense materials, for example lead, gives rise to secondary emission of X-rays via Bremsstrahlung, breaking radiation. Therefore shielding must be accomplished with low-density materials, for example plexiglas, lucite, other plastics, water, or, when transparency is not required, even wood. 33P, a beta emitter, 0.25 MeV, with a half-life of 25.4 days. It is used in life science laboratories in applications in which lower energy beta emissions are advantageous, such as DNA sequencing.
Occurrence.
Phosphorus is not found free in nature, but it is widely distributed in many minerals, mainly phosphates. Historically important but limited commercial sources were organic, such as bone ash and, in the latter 19th century, guano. Inorganic phosphate rock, which is partially made of apatite, an impure tricalcium phosphate mineral, is today the chief commercial source of this element. According to the U.S. Geological Survey, USGS, about 50% of the global phosphorus reserves are in the Arab nations. Large deposits of apatite are located in China, Russia, Morocco, Florida, Idaho, Tennessee, Utah, and elsewhere. Albright and Wilson in the UK and their Niagara Falls plant, for instance, were using phosphate rock in the 1890s and 1900s from Tennessee, Florida, and the Îles du Chromatable, Guano Island sources of phosphate. By 1950 they were using phosphate rock mainly from Tennessee and North Africa. In the early 1990s, Albright and Wilson's purified wet phosphoric acid business was being adversely affected by phosphate rock sales by China and the entry of their long-standing Moroccan phosphate suppliers into the purified wet phosphoric acid business. In 2012, the USGS estimated 71 billion tons of world reserves, where reserve figures refer to the amount assumed recoverable at current market prices. 0.19 billion tons were mined in 2011. Critical to contemporary agriculture, its annual demand is rising nearly twice as fast as the growth of the human population. Recent reports suggest that production of phosphorus may have peaked, leading to the possibility of global shortages by 2040. In 2007, at the rate of consumption, the supply of phosphorus was estimated to run out in 345 years. However, some scientists now believe that a peak phosphorus will occur in 30 years and that at current rates, reserves will be depleted in the next 50 to 100 years. Co-founder of Boston-based investment firm and environmental foundation Jeremy Grantham wrote in Nature in November 2012, that consumption of the element must be drastically reduced in the next 20 to 40 years or we will begin to starve. According to N. Greenwood and A. Earnshaw, authors of the textbook, Chemistry of the Elements, however, phosphorus comprises about 0.1% by mass of the average rock, and consequently the Earth's supply is vast, although dilute. This book, however, was published in 1997.
Research into urine diversion.
Urine contains most, 94% according to Wolgast, of the NPK nutrients excreted by the human body. Conversely, concentrations of heavy metals such as lead, mercury, and cadmium, commonly found in solid human waste, are much lower in urine, although not low enough to qualify for use in organic agriculture under current EU rules. The more general limitations to using urine as fertilizer then depend mainly on the potential for buildup of excess nitrogen, due to the high ratio of that macronutrient, and inorganic salts such as sodium chloride, which are also part of the wastes excreted by the renal system. The degree to which these factors impact the effectiveness depends on the term of use, salinity tolerance of the plant, soil composition, addition of other fertilizing compounds, and quantity of rainfall or other irrigation. Urine typically contains 70% of the nitrogen and more than half the phosphorus and potassium found in urban wastewater flows, while making up less than 1% of the overall volume. Thus far, source separation, or urine diversion and on-site treatment has been implemented in South Africa, China, and Sweden among other countries, with the Bill and Melinda Gates Foundation provided some of the funding implementations. China reportedly had 685,000 operating source separation toilets spread out among 17 provinces in 2003. Urine management is a relatively new way to view closing the cycle of agricultural nutrient flows and reducing sewage treatment costs and ecological consequences such as eutrophication resulting from the influx of nutrient-rich effluent into aquatic or marine ecosystems. Proponents of urine as a natural source of agricultural fertilizer claim the risks to be negligible or acceptable. Their views seem to be backed by research showing there are more environmental problems when it is treated and disposed of compared with when it is used as a resource. It is unclear whether source separation, urine diversion, and on-site urine treatment can be made cost-effective, nor whether required behavioral changes would be regarded as socially acceptable, as the largely successful trials performed in Sweden may not readily generalize to other industrialized societies. In developing countries, the use of whole raw sewage, night soil, has been common throughout history, yet the application of pure urine to crops is rare. Increasingly there are calls for urine's use as a fertilizer, such as a 2010 Scientific American article Human Urine is an Effective Fertilizer.
Production.
The majority of phosphorus-containing compounds are produced for use as fertilizers. For this purpose, phosphate-containing minerals are converted to phosphoric acid. Two distinct routes are employed, the main one being treatment of phosphate minerals with sulfuric acid. The other process utilizes white phosphorus, which may be produced by reaction and distillation from very low-grade phosphate sources. The white phosphorus is then oxidized to phosphoric acid and subsequently neutralized with base to give phosphate salts. Phosphoric acid obtained via white phosphorus is relatively pure and is the main source of phosphates used in detergents and other non-fertilizer applications.
Elemental phosphorus.
Presently, about 1 million short tons, 910,000 t, of elemental phosphorus is produced annually. Calcium phosphate, phosphate rock, mostly mined in Florida and North Africa, can be heated to 1,200 to 1,500 degc with sand, which is mostly CO2, and coke, impure carbon, to produce vaporized P4. The product is subsequently condensed into a white powder underwater to prevent oxidation by air. Even underwater, white phosphorus is slowly converted to the more stable red phosphorus allotrope. The chemical equation for this process when starting with fluoroapatite, a common phosphate mineral, is. Side products from this production include ferrophosphorus, a crude form of Fe2P, resulting from iron impurities in the mineral precursors. The silicate slag is a useful construction material. The fluoride is sometimes recovered for use in water fluoridation. More problematic is a mud containing significant amounts of white phosphorus. Production of white phosphorus is conducted in large facilities in part because it is energy intensive. The white phosphorus is transported in molten form. Some major accidents have occurred during transportation. Train derailments at Brownston, Nebraska and Miamisburg, Ohio led to large fires. The worst incident in recent times was an environmental one in 1968 when the sea became contaminated due to spillages and/or inadequately treated sewage from a white phosphorus plant at Placentia Bay, Newfoundland. Another process by which elemental phosphorus is extracted includes applying at high temperatures, 1500 degc. Thermphos International is Europe's only producer of elemental phosphorus with the annual capacity of 80,000 t provided by a plant at Vlissingen, Netherlands. Historically, before technology allowed mineral-based extractions, white phosphorus was isolated on an industrial scale from bone ash. In this scheme the tricalcium phosphate in bone ash is converted to monocalcium phosphate with sulfuric acid. Monocalcium phosphate is then dehydrated to the corresponding metaphosphate. Calcium metaphosphate yields, when ignited to a white heat with charcoal, 2/3 of its weight of white phosphorus while 1/3 of the phosphorus remains in the residue as calcium orthophosphate.
Compounds. Oxycids of phosphorus.
Phosphorus oxycids are extensive, often commercially important, and sometimes structurally complicated. They all have acidic protons bound to oxygen atoms and some have non-acidic protons that are bonded directly to phosphorus. Although many oxycids of phosphorus are formed, only 9 are important, and 3 of them, hyperphosphorus acid, phosphorus acid, and phosphoric acid, are particularly important ones.
Phosphorus V, Compounds. Oxides.
The most prevalent compounds of phosphorus are derivatives of phosphate, PO43, a tetrahedral anion. Phosphate is the conjugate base of phosphoric acid, which is produced on a massive scale for use in fertilizers. Being triprotic, phosphoric acid converts stepwise to 3 conjugate bases. Phosphate exhibits the tendency to form chains and rings with POP bonds. Many polyphosphates are known, including ATP. Polyphosphates arise by dehydration of hydrogen phosphates such as HPO42 and H2PO4. For example, the industrially important trisodium triphosphate, also known as sodium tripolyphosphate, STPP, is produced industrially on a megaton scale via this condensation reaction. Phosphorus pentoxide, P4O10, is the acid anhydride of phosphoric acid, but several intermediates are known between the two. This waxy white solid reacts vigorously with water. With metal cations, phosphate forms a variety of salts. These solids are polymeric, featuring POM linkages. When the metal cation has a charge of 2+ or 3+, the salts are generally insoluble, hence they exist as common minerals. Many phosphate salts are derived from hydrogen phosphate, HPO42. PCl5 and PF5 are common compounds. Both are volatile and pale or colorless. The other two halides, PBr5 and PI5 are unstable. The pentachloride and pentafluoride adopt trigonal bipyramid molecular geometry and are Lewis acids. With fluoride, PF5 forms PF6, an anion that is isoelectronic with SF6. The most important oxhalide is phosphorus oxychloride, POCl3, which is tetrahedral. Before extensive computer calculations were feasible, it was proposed that bonding in phosphorus, B, compounds involve d orbitals. It is now accepted that the bonding can be better explained by molecular orbital theory and involves only s and p orbitals on phosphorus.
Nitrides.
Compounds of the formula, PnCl2, N exist mainly as rings such as the trimer hexachlorophosphazane. The phosphazanes arise by treatment of phosphorus pentachloride with ammonium chloride, PCl5 plus NH4Cl, 1/N, NPCl2, N plus 4HCl. The chloride groups can be replaced by alkoxide, RO, to give rise to a family of polymers with potentially useful properties.
Sulfides.
Phosphorus forms a wide range of sulfides, where phosphorus can be P, B, P3, or other oxidation states. Most famous is the threefold symmetric P4S3 used in strike anywhere matches. P4S10 and P4O10 have analogous structures.
Phosphorus III compounds.
Phosphine, penthouse 3, and its organic derivatives, PO3, are structural analogues with ammonia, NH3, but the bond angles at phosphorus are closer to 90 deg for phosphine and its organic derivatives. It is an ill-smelling, toxic compound. Phosphine is produced by hydrolysis of calcium phosphide, California, 3P2. Unlike ammonia, phosphine is oxidized by air. Phosphine is also far less basic than ammonia. All four symmetrical triolids are well known: gaseous PF3, the yellowish liquids PCl3 and PBr3, and the solid PI3. These materials are moisture sensitive, hydrolyzing to give phosphorus acid. The trichloride, a common reagent, is produced by chlorination of white phosphorus. The trifluoride is produced from the trichloride by halide exchange. PF3 is toxic because it binds to hemoglobin. Phosphorus, 3, oxide, P4O6, also called tetraphosphorus hexoxide, is the anhydride of POH3, the minor tautomer of phosphorus acid. The structure of P4O6 is like that of P4O10 less the terminal oxide groups. Mixed oxhalides and oxhydrides of phosphorus, 3, are almost unknown.
Organophosphorus compounds.
compounds with PC and POC bonds are often classified as organophosphorus compounds. They are widely used commercially. The PCl3 serves as a source of P3+ en routes to organophosphorus 3 compounds. For example, it is the precursor to triphenylphosphine. Treatment of phosphorus triolids with alcohols and phenols gives phosphites, for example triphenyl phosphite. Similar reactions occur for phosphorus oxychloride, affording triphenyl phosphate.
Phosphorus I and phosphorus II compounds.
These compounds generally feature PP bonds. Examples include catenated derivatives of phosphine and organophosphines. The highly flammable gas diphosphine, P2H4, is the first of a series of derivatives of this type. Diphosphine is an analogue of hydrazine. Compounds containing P equals P double bonds have also been observed, although they are rare.
Phosphides.
The phosphide ion is P3. Phosphides arise by reaction of metals with red phosphorus. Salts of P3 do not exist in solution and these derivatives are refractory, reflecting their high lattice energy. Illustrated by the behavior calcium phosphide, many metal phosphides hydrolyze in water with release of phosphine. Schreibersite is a naturally occurring phosphide found in meteorites. Many polyphosphides are known, such as derivatives of OsP2. These can be structurally complex, ranging from Na3P7 and derivatives of P264. Often these species adopt cage-like structures that resemble fragments of violet phosphorus.
Spelling and etymology.
The name Phosphorus in ancient Greece was the name for the planet Venus and is derived from the Greek words, phos equals light, phero equals carry, which roughly translates as light bringer or light carrier. In Greek mythology and tradition, Agerinos equals morning star, in use until today. Hesperus or Hesperinus, Hesperus or Hesperinos or Aposporites equals evening star, in use until today, and Eosphorus, Eosphoros equals dawn bearer, not in use for the planet after Christianity, are close homologues, and also associated with Phosphorus the planet. According to the Oxford English Dictionary, the correct spelling of the element is phosphorus. The word phosphorus is the adjectival form of the P3+ valence, so, just as sulfur forms sulfurous and sulfuric compounds, phosphorus forms phosphorus compounds, for example, phosphorus acid, and P5+ valence phosphoric compounds, for example, phosphoric acids and phosphates.
History and discovery.
Phosphorus was the 13th element to be discovered. For this reason, and also due to its use in explosives, poisons and nerve agents, it is sometimes referred to as the devil's element. It was the first element to be discovered that was not known since ancient times. The discovery of phosphorus is credited to the German alchemist Henrik Brand in 1669, although other chemists might have discovered phosphorus around the same time. Brand experimented with urine, which contains considerable quantities of dissolved phosphates from normal metabolism. Working in Hamburg, Brand attempted to create the fabled philosopher's stone through the distillation of some salts by evaporating urine, and in the process produced a white material that glowed in the dark and burned brilliantly. It was named Phosphorus mirabilis, miraculous bearer of light. His process originally involved letting urine stand for days until it gave off a terrible smell. Then he boiled it down to a paste, heated this paste to a high temperature, and led the vapors through water, where he hoped they would condense to gold. Instead, he obtained a white, waxy substance that glowed in the dark. Brand had discovered phosphorus. We now know that Brand produced ammonium sodium hydrogen phosphate, NH4, now HPO4. While the quantities were essentially correct, it took about 1,100 liters of urine to make about 60 g of phosphorus. It was unnecessary to allow the urine to rot. Later scientists discovered that fresh urine yielded the same amount of phosphorus. Brand at first tried to keep the method secret, but later sold the recipe for 200 thalers to D. Kraft from Dresden, who could now make it as well, and toured much of Europe with it, including England, where he met with Robert Boyle. the secret that it was made from urine leaked out, and first Johann Kuhnkel, 1630–1703, in Sweden, 1678, and later Boyle in London, 1680, also managed to make phosphorus, possibly with the aid of his assistant, Ambrose Godfrey Hankwitz, who later made a business of the manufacture of phosphorus. Boyle states that Kraft gave him no information as to the preparation of phosphorus other than that it was derived from somewhat that belonged to the body of man. This gave Boyle a valuable clue, so that he too managed to make phosphorus, and published the method of its manufacture. Later he improved Brand's process by using sand in the reaction, still using urine as base material. Robert Boyle was the first to use phosphorus to ignite sulfur-tipped wooden splints, forerunners of our modern matches, in 1680. In 1769 Johann Gottlieb Gahn and Carl Wilhelm Scheele showed the calcium phosphate, Ca. 3, Po. 4, 2, is found in bones, and they obtained elemental phosphorus from bone ash. Antoine Lavoisier recognized phosphorus as an element in 1777. Bone ash was the major source of phosphorus until the 1840s. The method started by roasting bones, then employed the use of clay retorts encased in a very hot brick furnace to distill out the highly toxic elemental phosphorus product. Alternately, precipitated phosphates could be made from ground-up bones that had been degreased and treated with strong acids. White phosphorus could then be made by heating the precipitated phosphates, mixed with ground coal or charcoal in an iron pot, and distilling off phosphorus vapor in a retort. Carbon monoxide and other flammable gases produced during the reduction process were burnt off in a flare stack. In the 1840s, world phosphate production turned to the mining of tropical island deposits formed from bird and bat guano, see also Guano Islands Act. These became an important source of phosphates for fertilizer in the latter half of the 19th century. Phosphate rock, a mineral containing calcium phosphate, was first used in 1850 to make phosphorus, and following the introduction of the electric arc furnace in 1890, elemental phosphorus production switched from the bone ash heating, to electric arc production from phosphate rock. After the depletion of world guano sources about the same time, mineral phosphates became the major source of phosphate fertilizer production. Phosphate rock production greatly increased after World War II, and remains the primary global source of phosphorus and phosphorus chemicals today. See the article on peak phosphorus for more information on the history and present state of phosphate mining. Phosphate rock remains a feedstock in the fertilizer industry, where it is treated with sulfuric acid to produce various superphosphate fertilizer products. White phosphorus was first made commercially in the 19th century for the match industry. This used bone ash for a phosphate source, as described above. The bone ash process became obsolete when the submerged arc furnace for phosphorus production was introduced to reduce phosphate rock. The electric furnace method allowed production to increase to the point where phosphorus could be used in weapons of war. In World War I it was used in incendiaries, smoke screens and tracer bullets. A special incendiary bullet was developed to shoot at hydrogen-filled zeppelins over Britain, hydrogen being highly flammable. During World War II, Molotov cocktails made of phosphorus dissolved in petrol were distributed in Britain to specially selected civilians within the British resistance operation, for defence. And phosphorus incendiary bombs were used in war on a large scale. Burning phosphorus is difficult to extinguish, and if it splashes onto human skin it has horrific effects. Early matches used white phosphorus in their composition, which was dangerous due to its toxicity. Murders, suicides and accidental poisonings resulted from its use. An apocryphal tale tells of a woman attempting to murder her husband with white phosphorus in his food, which was detected by the stews giving off luminous steam. In addition, exposure to the vapors gave match workers a severe necrosis of the bones of the jaw, the infamous phossy jaw. When a safe process for manufacturing red phosphorus was discovered, with its far lower flammability and toxicity, laws were enacted, under the Berne Convention, 1906, requiring its adoption as a safer alternative for match manufacture. The toxicity of white phosphorus led to discontinuation of its use in matches. The Allies used phosphorus incendiary bombs in World War II to destroy Hamburg, the place where the miraculous bearer of light was first discovered.
Glow.
It was known from early times that the green glow emanating from white phosphorus would persist for a time in a stoppered jar, but then cease. Robert Boyle in the 1680s ascribed it to debilitation of the air. In fact, it is oxygen being consumed. By the 18th century, it was known that in pure oxygen, phosphorus does not glow at all. There is only a range of partial pressure at which it does. Heat can be applied to drive the reaction at higher pressures. In 1974, the glow was explained by J. Van Zee and A. U. Khan. A reaction with oxygen takes place at the surface of the solid, or liquid, phosphorus, forming the short-lived molecules HPO and P2O2 that both emit visible light. The reaction is slow and only very little of the intermediates are required to produce the luminescence, hence the extended time the glow continues in a stoppered jar. Since that time, phosphors and phosphorescence were used loosely to describe substances that shine in the dark without burning. Although the term phosphorescence was originally coined as a term by analogy with the glow from oxidation of elemental phosphorus, it is now reserved for another fundamentally different process, re-emission of light after illumination.
Applications. Fertilizer.
The dominant application of phosphorus is in fertilizers, which provides phosphate as required for all life and is often a limiting nutrient for crops. Phosphorus, being an essential plant nutrient, finds its major use as a constituent of fertilizers for agriculture and farm production in the form of concentrated phosphoric acids, which can consist of 70% to 75% P2O5. Global demand for fertilizers led to large increase in phosphate, PO43 production in the second half of the 20th century. Due to the essential nature of phosphorus to living organisms, the low solubility of natural phosphorus-containing compounds, and the slow natural cycle of phosphorus, the agricultural industry relies on fertilizers that contain phosphate. A major form of these fertilizers is superphosphate of lime, a mixture of two salts, calcium dihydrogen phosphate Ca, H2PO4, 2 and calcium sulfate dihydrate Ca-SO4 produced by the reaction of sulfuric acid and water with calcium phosphate.
Organophosphorus compounds.
White phosphorus is widely used to make organophosphorus compounds, through the intermediates phosphorus chlorides and 2-phosphorus sulfides, phosphorus pentasulfide, and phosphorus sesquisulfide. Organophosphorus compounds have many applications, including in plasticizers, flame retardants, pesticides, extraction agents, and water treatment.
Metallurgical aspects.
Phosphorus is also an important component in steel production, in the making of phosphor bronze, and in many other related products. Phosphorus is added to metallic copper during its smelting process to react with oxygen present as an impurity in copper and to produce phosphorus-containing copper, CuOFP, alloys with a higher hydrogen embrittlement resistance than normal copper.
Matches.
Phosphorus-contained matches were first produced in the 1830s and contained a mixture of white phosphorus, an oxygen-releasing compound, potassium chlorate, lead dioxide or some nitrate, and a binder in their heads. They were rather sensitive to storage conditions, toxic and unsafe, as they could be lit by striking on any rough surface. Therefore, their production was gradually banned between 1872 and 1925 in different countries. The International Berne Convention, adopted in 1906, prohibited the use of white phosphorus in matches. As a consequence, the Strike Anywhere matches were gradually replaced by safety matches where white phosphorus was replaced by phosphorus sesquisulfide, P4S3, sulfur or antimony sulfide. Such matches are hard to ignite on an arbitrary surface and require a special strip. The strip contains red phosphorus which heats up upon striking, reacts with the oxygen-releasing compound in the head and ignites the flammable material of the head.
Water softening.
Sodium tripolyphosphate made from phosphoric acid is used in laundry detergents in some countries, but banned for this use in others. It is useful for softening water to enhance the performance of the detergents and to prevent pipe boiler tube corrosion.
Niche applications.
Phosphates are utilized in the making of special glasses that are used for sodium lamps. Bone ash, calcium phosphate, is used in the production of fine china. Phosphoric acid made from elemental phosphorus is used in food applications such as some soft drinks. The acid is also a starting point to make food-grade phosphates. These include monocalcium phosphate that is employed in baking powder and sodium tripolyphosphate and other sodium phosphates. Among other uses, these are used to improve the characteristics of processed meat and cheese. Others are used in toothpaste. White phosphorus, called WP, slang term Willy Peter, is used in military applications as incendiary bombs, for smoke screening as smoke pots and smoke bombs, and in tracer ammunition. It is also a part of an obsolete M34 white phosphorus U.S. hand grenade. This multi-purpose grenade was mostly used for signaling, smoke screens and inflammation. It could also cause severe burns and had a psychological impact on the enemy. Military uses of white phosphorus are constrained by international law. In trace amounts, phosphorus is used as a dopant for N-type semiconductors. 32P and 33P are used as radioactive tracers in biochemical laboratories. Phosphate is a strong complexing agent for the hexavalent uranyl, UO22+ species, and this is the reason why apatite and other natural phosphates can often be very rich in uranium. Tributyl phosphate is an organophosphate soluble in kerosene and used to extract uranium in the Purex process applied in the reprocessing of spent nuclear fuel.
Biological role.
Inorganic phosphorus in the form of the phosphate PO3. 4 is required for all known forms of life, playing a major role in biological molecules such as DNA and RNA, where it forms part of the structural framework of these molecules. Living cells also use phosphate to transport cellular energy in the form of adenosine triphosphate, ATP. Nearly every cellular process that uses energy obtains it in the form of ATP. ATP is also important for phosphorylation, a key regulatory event in cells. Phospholipids are the main structural components of all cellular membranes. Calcium phosphate salts assist in stiffening bones. Living cells are defined by a membrane that separates it from its surroundings. Biological membranes are made from a phospholipid matrix and proteins, typically in the form of a bilayer. Phospholipids are derived from glycerol, such that 2 of the glycerol hydroxyl, OH, protons have been replaced with fatty acids as an ester, and the 3rd hydroxyl proton has been replaced with phosphate bonded to another alcohol. An average adult human contains about 0.7 kilograms of phosphorus, about 85 to 90% of which is present in bones and teeth in the form of apatite, and the remainder in soft tissues and extracellular fluids, 1%. The phosphorus content increases from about 0.5 weight% in infancy to 0.65-1.1 weight% in adults. Average phosphorus concentration in the blood is about 0.4 grams per liter, about 70% of that is organic and 30% inorganic phosphates. A well-fed adult in the industrialized world consumes and excretes about 1 to 3 grams of phosphorus per day, with consumption in the form of inorganic phosphate and phosphorus-containing biomolecules such as nucleic acids and phospholipids. And excretion almost exclusively in the form of phosphate ions such as H2PO4 and HPO2. 4. Only about 0.1% of body phosphate circulates in the blood, and this amount reflects the amount of phosphate available to soft tissue cells.
Bone and teeth enamel.
The main component of bone is hydroxyapatite as well as amorphous forms of calcium phosphate, possibly including carbonate. Hydroxyapatite is the main component of tooth enamel. Water fluoridation enhances the resistance of teeth to decay by the partial conversion of this mineral to the still harder material called fluoroapatite.
Phosphorus deficiency.
In medicine, low phosphate syndromes are caused by malnutrition, by failure to absorb phosphate, and by metabolic syndromes that draw phosphate from the blood, such as refeeding after malnutrition, or pass too much of it into the urine. All are characterized by hyperphosphatemia, which is a condition of low levels of soluble phosphate levels in the blood serum, and therefore inside cells. Symptoms of hyperphosphatemia include muscle and neurological dysfunction, and disruption of muscle and blood cells due to lack of ATP. Too much phosphate can lead to diarrhea and calcification, hardening, of organs and soft tissue, and can interfere with the body's ability to use iron, calcium, magnesium, and zinc. Phosphorus is an essential macromineral for plants, which is studied extensively in edaphology in order to understand plant uptake from soil systems. In ecological terms, phosphorus is often a limiting factor in many environments. That is, the availability of phosphorus governs the rate of growth of many organisms. In ecosystems, an excess of phosphorus can be problematic, especially in aquatic systems, resulting in eutrophication which sometimes lead to algal blooms.
Food sources.
The main food sources for phosphorus are foods containing protein, although proteins do not contain phosphorus. For example, milk, meat, and soya typically also have phosphorus. As a rule, if one holds a meal plan providing sufficient amount of protein and calcium, then the amount of phosphorus is also likely sufficient.
Precautions.
Organic compounds of phosphorus form a wide class of materials. Many are required for life, but some are extremely toxic. Fluorophosphate esters are among the most potent neurotoxins known. A wide range of organophosphorus compounds are used for their toxicity to certain organisms as pesticides, herbicides, insecticides, fungicides, etc., and weaponized as nerve agents. Most inorganic phosphates are relatively non-toxic and essential nutrients. The white phosphorus allotrope presents a significant hazard because it ignites in air and produces phosphoric acid residue. Chronic white phosphorus poisoning leads to necrosis of the jaw called phossy jaw. Ingestion of white phosphorus may cause a medical condition known as smoking stool syndrome. Upon exposure to elemental phosphorus, in the past it was suggested to wash the affected area with 2% copper sulfate solution to form harmless compounds that can be washed away. According to the recent U.S. Navy's Treatment of Chemical Agent Casualties and Conventional Military Chemical Injuries, FM 8-285, Part 2 Conventional Military Chemical Injuries, cupric, copper, 2-sulfate has been used by U.S. personnel in the past and is still being used by some nations. However, copper sulfate is toxic and its use will be discontinued. Copper sulfate may produce kidney and cerebral toxicity as well as intravascular hemolyses. The manual suggests instead a bicarbonate solution to neutralize phosphoric acid, which will then allow removal of visible white phosphorus. Particles often can be located by their emission of smoke when air strikes them, or by their phosphorescence in the dark. In dark surroundings, fragments are seen as luminescent spots. Promptly debride the burn if the patient's condition will permit removal of bits of WP, white phosphorus, that might be absorbed later and possibly produce systemic poisoning. Do not apply oily-based ointments until it is certain that all WP has been removed. Following complete removal of the particles, treat the lesions as thermal burns. As white phosphorus readily mixes with oils, any oily substances or ointments are not recommended until the area is thoroughly cleaned and all white phosphorus removed.
USDA List I status.
Phosphorus can reduce elemental iodine to hydrochloric acid, which is a reagent effective for reducing ephedrine or pseudoephedrine to methamphetamine. For this reason, red and white phosphorus were designated by the United States Drug Enforcement Administration as List I precursor chemicals under 21 CFR 1310.02 effective on November 17, 2001. As a result, in the United States, handlers of red or white phosphorus are subject to stringent regulatory controls. Phosphorus is highly reactive and ignites at about 300 DEGC, though it is still more stable than white phosphorus, which ignites at about 30 degc. After prolonged heating or storage, the color darkens, see info box images. The resulting product is more stable and does not spontaneously ignite in air.
Violet phosphorus.
Violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 degc. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, a red-purple form is obtained. Therefore this form is sometimes known as Hittorf's phosphorus, or violet or a metallic phosphorus.
Black phosphorus.
Black phosphorus is the least reactive allotrope and the thermodynamically stable form below 550 degc. It is also known as bimetallic phosphorus and has a structure somewhat resembling that of graphite. High pressures are usually required to produce black phosphorus, but it can also be produced at ambient conditions using metal salts as catalysts.
Isotopes.
23 isotopes of phosphorus are known, including all possibilities from 24P up to 46P. Only 31P is stable and is therefore present at 100% abundance. The half-integer nuclear spin and high abundance of 31P make phosphorus 31nm spectroscopy a very useful analytical tool and historically first isolated from human urine, and bone ash was an important early phosphate source. Phosphate minerals are fossils. Low phosphate levels are an important limit to growth in some aquatic systems. The chief commercial use of phosphorus compounds for production of fertilizers is due to the need to replace the phosphorus that plants remove from the soil, and its annual demand is rising nearly twice as fast as the growth of the human population.
Characteristics. Physical.
Phosphorus exists as several forms, allotropes, that exhibit strikingly different properties. The two most common allotropes are white phosphorus and red phosphorus. Another form, scarlet phosphorus, is obtained by allowing a solution of white phosphorus and carbon disulfide to evaporate in sunlight. Black phosphorus is obtained by heating white phosphorus under high pressures, about 12,000 standard atmospheres or 1.2 gigapascals. In appearance, properties, and structure, it resembles graphite, being black and flaky, a conductor of electricity, and is puckered sheets of linked atoms. Another allotrope is diphosphorus. It contains a phosphorus dimer as a structural unit and is highly reactive.
White phosphorus and related molecular forms.
The most important form of elemental phosphorus from the perspective of applications in the chemical literature is white phosphorus, often abbreviated as WP. It consists of tetrahedral P, fours and at their vertices. White phosphorus is insoluble in water but soluble in carbon disulfide. The molasses, cracking, of P4 at 1100 Kelvin, gives diphosphorus, P2. This species is not stable as a solid or liquid. The dimeric unit contains a triple bond and is analogous to N2. It can also be generated as a transient intermediate in solution by the molasses of organophosphorus precursor reagents. At still higher temperatures, P2 dissociates into atomic P. Although the term phosphorescence is derived from phosphorus, the reaction that gives phosphorus its glow is properly called chemiluminescence, glowing due to a cold chemical reaction, not phosphorescence, re-emitting light that previously fell onto a substance and excited it.
Red phosphorus.
Red phosphorus is polymeric in structure. It can be viewed as a derivative of P4 wherein one pp bond is broken, and one additional bond is formed with a neighboring tetrahedron resulting in a chain-like structure. Red phosphorus may be formed by heating white phosphorus to 250 degc, 482 degF, or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. In this sense, red phosphorus is not an allotrope, but rather an intermediate phase between the white and violet phosphorus, and most of its properties have a range of values. For example, freshly prepared, bright red ore molecules, in which each atom is bound to the other 3 atoms by a single bond. This p,4 tetrahedron is also present in liquid and gaseous phosphorus up to the temperature of 800 degc when it starts decomposing to p,2 molecules. Solid white exists in 2 forms. At low temperatures, the B form is stable. At high temperatures the A form is predominant. These forms differ in terms of the relative orientations of the constituent p4 tetrahedra. White phosphorus is the least stable, the most reactive, the most volatile, the least dense, and the most toxic of the allotropes. White phosphorus gradually changes to red phosphorus. This transformation is accelerated by light and heat, and samples of white phosphorus almost always contain some red phosphorus and accordingly appear yellow. For this reason, white phosphorus that is aged or otherwise impure, for example weapons-grade not lab-grade WP, is also called yellow phosphorus. White phosphorus glows in the dark, when exposed to oxygen, with a very faint tinge of green and blue, is highly flammable and pyrophoric, self-igniting, upon contact with air and is toxic, causing severe liver damage on ingestion. Owing to its pyrophoricity, white phosphorus is used as an additive in napalm. The odor of combustion of this form has a characteristic garlic smell, and samples are commonly coated with white, phosphorus pentoxide, which consists of p,4O, 10 tetrahedra with oxygen inserted between the phosphorus atoms.
Phosphorus.
Phosphorus is a non-metallic chemical element with symbol P and atomic number 15. A multivalent pnictogon, phosphorus as a mineral is almost always present in its maximally oxidized state, as in organic phosphate rocks. Elemental phosphorus exists in 2 major forms, white phosphorus and red phosphorus, but due to its high reactivity, phosphorus is never found as a free element on Earth. The first form of elemental phosphorus to be produced, white phosphorus, in 1669, emits a faint glow upon exposure to oxygen, hence its name given from Greek mythology, phosphoros meaning light bearer, Latin Lucifer, referring to the morning star, the planet Venus. The term phosphorescence, meaning glow after illumination, originally derives from this property of phosphorus, although this word has since been used for a different physical process that produces a glow. The glow of phosphorus itself originates from oxidation of the white, but not red, phosphorus, a process now termed chemiluminescence. The vast majority of phosphorus compounds are consumed as fertilizers. Other applications include the role of organophosphorus compounds in detergents, pesticides and nerve agents, and matches. Phosphorus is essential for life. As phosphate, it is a component of DNA, RNA, ATP, and also the phospholipids that form all cell membranes. Demonstrating the link between phosphorus and life, elemental phosphorus was